So the last one is going to be the van der Waals forces, or also called London dispersion forces. Now, look at this because this is kind of difficult for you to understand, okay? Let's pretend that I have an atom of argon. And argon is a gas, yes? But how can we liquidify argon? For liquidifying argon, we need some kind of force that attracts them together. So we are going to analyze what happens. In the van der Waals forces or London dispersion forces, we are going to talk about only molecules that are non-polar. Okay? If the molecules are non-polar, or in this case we have only an atom of argon, but we can do the same with the hydrogen. Okay, we put hydrogen, hydrogen, and you can see that this molecule is symmetric, yes? But what happens with this? The explanation, so we are talking about molecules that are non-polar. What happens is that these electrons that are floating around, yes, that are moving around the argon, they are not moving in a circle. They are not moving at the same speed. They are not projecting any path or any pattern that we can follow. The problem is that, so sometimes and temporarily, like a millisecond, some of the electrons are going to be located more on the left of the molecule, or in this case of the atom. The same here. Maybe 90% of the time or 99% of the time, the cloud of electrons is going to be evenly distributed. But at some point, because we don't know where the electrons are, maybe the cloud of electrons are going to be concentrated in one side. If they do concentrate in one side, we are going to form what we call a temporary dipole. The temporary dipole is going to act. Do you remember when we saw the metallic bond that we said how with the magnet you attracted the electrons of a nail? So the atoms at the tip of the nail were going to be bare of electrons, and they will attract another nail, and another nail, and another nail. Well, this is the same thing. The temporary dipole is going to produce in another molecule that maybe is close to it. I'm going to move this a little bit so you can see this better. Let me move this, although it's not very nice, but it helps us. Okay, so if I have another molecule of hydrogen here, guess what? I have this temporary dipole, yes, this one, that is going to produce an induced dipole. In other words, it's going to happen the same as the magnet and the eclipse. Yes? So it's going to, this part is going to become what we call a density positive, and this is going to be a density negative. It doesn't have, this is density. Yes? Do you remember that weird letter? Okay? So this is going to attract the electrons in this direction, and that is going to be a chain of electrons that are going to be forming an induced dipole. Of course, I'm going to have that intermolecular force in between these molecules, but that is super, super weak. These are the weakest ones. That's why even non-polar liquids can be boiled at very low temperature, comparing with the same structure with a higher intermolecular force. So let's rewind. Yes, we have the intermolecular forces only work with discrete molecules. if the molecule is polar and is not oxygen, nitrogen, or fluorine, we are going to have a dipole-dipole compound. Yes, so we are going to have a dipole-dipole intermolecular force. And if in the particular case that the molecule has hydrogen and is attached to oxygen, nitrogen, or fluorine, we are going to have a special intermolecular force that is not, it should be called dipole-dipole, but since hydrogen is involved, we are going to call that hydrogen bond. And it's always happening between the lone pairs in one molecule with the hydrogen in another or other molecule or in a different molecule. Yes? The most specific case is hydrogen fluoride or water or even ammonia. In the ammonia you have hydrogen, hydrogen, and hydrogen, and this pair of electrons is going to be attached. Look, I don't put the line, I put dashes with another hydrogen that belongs, of course, to another ammonia molecule. Okay, so we have like chains of molecules. And the last one is the van der Waals forces or London dispersion forces, where a molecule or an atom of a noble gas can be forming a temporary dipole because of the electrons moving all the time, and they are going to produce an induced dipole in the other one. Good? Okay. We talk about how the metals were. Yes? We did the structure of the metallic bonding. I think we did, but that is the only thing that we didn't cover today. So metallic bonding is in between metals, and basically is all the atoms that are going to be in a crystal lattice of, or a metallic lattice. Lattice is like a network, yes? Where we have the atoms without the valence electrons. The valence electrons are the last shell, yes? So let's say that we have magnesium here, so it's going to be magnesium 2 plus, magnesium 2 plus, magnesium 2 plus. Why 2 plus? Because the magnesium belongs in the second group and is exactly. So this magnesium is going to provide 2 electrons to the sea of electrons. This magnesium is going to provide 2 more, and this magnesium 2 more, and then this magnesium 2 more. So we are going to have millions of electrons because we have millions of atoms going around the metallic lattice. The electrons on the surface are going to be responsible for the shyness of the metals. The free electrons are also responsible for the conductivity of electricity and heat. Yes? And also because of this sea of electrons, do you remember that we said that we can write with the graphite because they could slide against each other? Where this one is the same thing, guys, because when we hammer or we pull the metal, these layers of metals can slide over each other. So when we, let's say, oops, that was not the thing that I wanted to do. When we take this, okay, and let's say hammer or pull it up, I'm going to be able to slide it. So we are going to have sliding over each other. That's why the metallics or the metals are malleable, meaning we can hammer it down into sheets, or they are ductile. And ductile means that they can be pulled